Hi everyone, today a video in the organic analysis series looking at infrared spectroscopy. So infrared spectroscopy is a technique that can be used to help identify compounds. If we have a pair of atoms that we've joined through a chemical bond, a covalent chemical bond, it's always vibrating. That bond will always be vibrating as long as we're not at 0 Kelvin, absolute zero. There'll always be some energy in that bond, and hence the bond will be vibrating. And so you can imagine it as two balls that are joined by a spring, and this will constantly be vibrating around that equilibrium sort of position. Now, the stronger the bond, the faster the vibration is. And if we have a faster vibration, we can think of it happening more times per second, and so we say that it occurs at a higher frequency. The converse is also true, so if we have a weaker bond, the slower the vibration is, and therefore it occurs at a lower frequency. Now also, the heavier the atom, the slower the bond vibrates. We can think of that simply as being that imagine it would take more energy to move if it's heavier. Imagine you were lifting something heavier, you'd probably do it slowly, more slower than if you had a lighter object. And so the heavier the atom, the slower the bond vibrates and has a lower frequency. And conversely, the lighter the atom, the faster it vibrates and the higher the frequency. But every bond will have a unique natural frequency, the natural frequency being what its naturally occurring frequency is. Now, when we fire infrared radiation through a sample, these bonds can absorb energy from that radiation. And if they absorb the energy, they vibrate more. Now, this will only occur if the frequency of this radiation that we fire through exactly matches that natural frequency of the bond. And so that the radiation that passes through the sample will be missing some frequencies. So normally we fire quite a wide range of infrared radiation, a wide range of frequencies of that through the sample. And when we look at the end, we'll find that there are some frequencies that are missing. These are the frequencies that have been absorbed by the bonds in the compound. And what this means is that if we have different types of bond, and hence different functional groups essentially, whether we have an OH bond or a CH bond or a CO bond, whatever it might be, these absorb different frequencies of infrared radiation. And hence we can distinguish them in an IR spectrum. And so our IR spectrum is really useful for telling us what functional groups we have in our molecule. Now, the peaks in an IR spectrum are actually dips because the radiation has been absorbed by the bond. And so we'll see in the examples, essentially we have this kind of baseline of 100%, and typically what we call a peak is actually a dip because it goes down because the radiation has been absorbed by the bond. And I've just written the equation here for what the frequency is. Essentially, the two variables in that, because the 1 and the 2 pi are all just constants, the K is something called the force constant, essentially how stiff the spring is. If we're imagining it as two balls on a spring, how stiff is that spring? If the bond if that spring is very, very stiff, we can imagine it to have a very high spring constant, and therefore we can imagine that being essentially a very strong bond. The other is M, which is the mass, essentially the masses of the things that we are dealing with. And so you can see from that formula that actually if we have a heavier atom, that frequency is going to be lower. A lighter atom would give a higher frequency. And if we have a stronger bond, that K is bigger and therefore a higher frequency. A weaker bond, a lower K, and therefore a lower frequency. And so in an infrared spectrometer, we have a beam that contains a wide range of IR frequencies. We pass it through the sample. The radiation that emerges has not been absorbed by the sample, and the stuff that doesn't must have been absorbed by the bonds. And so it reaches a detector. You can see here that typically we have an infrared source that gets split into two. One of it goes through our sample, one of it goes through a reference cell, just so that we eliminate any kind of things that are just naturally in the air that might absorb it, for example. These then go to a detector. Essentially, we look for the difference between the two. And this detector converts the signal into a graph of intensity of radiation emerging, something that we call transmittance, essentially how much has gone through, against the frequency of the radiation. Now the frequency, weirdly, is normally expressed as something called a wave number. So rather than just doing it as a frequency normally a frequency would be done in hertz. Instead, we express it as a wave number, and this wave number is normally measured in centimeters to the -1. So a wave number is simply the reciprocal of the wavelength, 1 over the wavelength, and we typically measure it in centimeters to get sort of easier numbers to work with out. So don't get confused by what you see on the x-axis. Essentially what you're seeing is similar to, because it's based off wavelength, it's also related to frequency, but essentially it is related to the frequency. It's just that we talk about it in wave number. So if you see this kind of V symbol with a line over the top, that is wave number, not frequency. But the two are related. Now, something that is not quite fully examinable on an A-level syllabus, but will hopefully make you understand some of this a bit better, is something that we call the vibrational modes. These essentially are how our molecules can vibrate. And so here we're taking this example of CO2, carbon dioxide. At equilibrium, you can see we have our two carbon-oxygen bonds here. They're depicted just as lines. Remember that carbon dioxide has carbon-oxygen double bonds. And you can see that generally carbon dioxide is a linear molecule. And so we'll have our equilibrium. There'll be a certain bond distance. Typically our bonds are, as we said, always vibrating. They're never static. But there will be an equilibrium position on average where they are. Now, if we absorb this radiation that is of the right frequency for this bond, it matches the natural frequency of these CO double bonds, we can get these bonds either vibrating more in a number of ways. Probably the easiest ways to think about it is to look at the stretching vibrations. So this is where we start off with our normal CO2 in the equilibrium position, and essentially we can have a symmetric stretch. So you can imagine both of those oxygens kind of going slightly further out symmetrically. That's our symmetric stretch. They could also come in symmetrically. We can have an asymmetric stretch. So this is where one of our carbon-oxygen bonds extends further than the other does, and so that's an asymmetric stretch. And then finally we have a bending mode. So this is where actually it isn't necessarily the bond lengths that are moving in and out, but instead they are maybe moving up and down, or sort of in and out of the plane, and that's called a bending mode. Now, we can work out how many vibrational modes we will see for a molecule by doing a simple calculation. And the simple calculation is that a non-linear molecule has 3n-6 vibrational modes. N is just the number of atoms we have in our molecule. For a linear molecule, we have 3n-5 vibrational modes. And so for our CO2, that's a linear molecule, so we would have 3 times 3 minus 5, which is 4. We'd expect to see 4 vibrational modes. And the 4 that we can see here is the symmetric CO stretch, 2 bends. Then these bends actually have the same frequency. They're what we call degenerate, but they are technically 2 different bends. They're just occurring at the same frequency. And then we have our asymmetric stretch. Now, the selection rule for IR spectroscopy, what we mean by this is, what do we have to happen to actually see a peak in our IR spectrum? Is that the vibration must involve a change in the dipole moment of the molecule. Now, if we think about CO2, we know that CO2 is a non-polar molecule, but we do have dipoles. We have our dipoles in the CO bonds. The oxygen is much more electronegative than the carbon is. So we have our dipole, our polar CO bond, but overall the molecule is not polar because the dipole going to the left cancels out the dipole going to the right because it's linear. Now what this actually means is if we think about our dipole on each of those carbon-oxygen bonds, if we have a symmetric stretch, the dipole is related to the charge times the distance. So if the distance changes, our dipole number changes. But if we go symmetrically in either direction, overall there's no change again. Because while we might have increased the dipole going to the left, we also increase the dipole going to the right. And they, because it's symmetric, cancel each other out. And so typically you do not see symmetric stretches in infrared spectrum. However, for bends and for typically asymmetric stretches, we do tend to see these because being asymmetric, overall the dipole moment of that molecule will change. But as I say, this is non-examinable. You don't need to know this for your A level, but hopefully maybe it helps you understand where some of these peaks come from. So here's an example of what an infrared spectrum looks like. This is the infrared spectrum here of methanol, CH4O, simplest alcohol. And as you can see, as we said, our peaks are actually dips. Along the bottom, we have this wave number measured in centimetres to the -1. And typically, spectra run from 4,000 down to about 500. Now you can see that this looks maybe going in the wrong direction. We have a higher number at the left, lower number at the bottom. So everything about an IR spectrum essentially is almost reversed. The peaks are actually dips. We have a higher number at the left, lower number at the right. But the y-axis is transmittance, how much of this radiation has come back through. And at the bottom, the wave number. You can think of it essentially as being the frequency. And you can see that generally along the top, we are kind of along that almost 100 line, that we call our baseline. And then we have these peaks for where our different types of bonds have absorbed that radiation. Now in the exam, you'll also be given something like is shown on the right, a table of absorption data. And this will give you the bond type, so for example an NH bond or an OH bond or a C double bond O. And it will give you the range in which typically that bond absorbs the infrared radiation. So for example, an OH in alcohols absorbs from 3,230 to 3,550 centimetres to the -1. A CO double bond goes from 1680 to 1750, for example. And so most of these examples that you see here are of the stretching vibration type that we talked about on the previous slide. Most of the ones in that table, certainly the higher up numbers, are stretching vibrations. Now, one really key takeaway message that I've highlighted here on this slide is that OH alcohol peaks are very broad. So methanol is an alcohol, and you can see that generally, if we look at the peak that's just after 1,000, the sort of peaks around 1,500, the peaks around 3,000, they're pretty sharp, clearly defined peaks. However, the one that's kind of 3,300, 3,400 is a very broad peak. And this is very characteristic of OH groups in alcohols. It's a very easy, this is why infrared is such a good technique for telling functional groups. You can tell right away that you have an OH group in your molecule. So OH peaks are very broad. But a key distinction to make here is that just because the range given on the table here says whatever range it says, it doesn't mean that the peak will span that range. So for alcohols, it is a very broad peak. So we have our wave number range here of 3,230 to 3,550. And if we look at our OH here, it generally sort of goes from roughly about 3,500 to roughly about 3,200. So it basically does actually occupy that full range of wave numbers because it's a broad peak. Most other peaks, though, are not broad. They're much more sharply defined. And so if we look for an example here, we'd have our CO peak is actually the one occurring at about 1,100-ish, that very sort of sharp peak down by about 1,000. That's actually our CO single bond vibration here. And you can see that the range that's given is 1,000 to 1,300. That doesn't mean that it stretches from 1,000 to 1,300, but that it can be found somewhere within that area. But most peaks are of this kind of quite sharp defined nature. OH peaks in alcohols are very broad and easy to spot. So if we have a look at some examples here of these infrared spectra, the first is this methanol. And so typically for A level, the one we need to be really caring about here is our OH alcohol stretch at 3,350. And it's very broad, as I said. It's very easy to be able to tell. Now there are some more non-examinable ones. It depends on what the table is given in the exam in terms of whether these are given to you on the table. But CH stretches always occur around 3,000. So here we have some at this peak at 2,900 and 2,800. We have this kind of sort of slightly less intense peak at around 1,500. They're typically CH bends, so not stretches this time, but bends. And then finally, we have that very sort of characteristic CO stretch at roughly 1,000 centimeters to the -1. The next one is methanoic acid. This is a carboxylic acid, CH2O2. Now, if we didn't know what the structure of this molecule was, what the bonding in it was, we could definitely use an IR spectrum to help us out here. You can see we have that very broad peak. And actually, you can see that the peak here looks incredibly broad because it's started to actually overlap with those CH stretches at about 2,900, 2,800. And so we have this exceptionally very broad peak. And this is pretty characteristic here of OH acids rather than OH alcohols, They're both very, very broad peaks, but OH acids tend to be slightly lower down, more towards 3000 rather than 3300, 3400, and they tend to therefore overlap with the CH stretches. So we have a very sort of characteristic OH broad stretch at about 3100. And then the other key one to note is we have a very, very intense peak at about 1700 centimeters to the -1. And this is really characteristic of a CO double bond stretch. So if we know that we've got a CO double bond and we know that we've got an OH group, that must be a carboxylic acid. There's also some more non-examinable ones. So the CH stretches at 2900 and 2800 that are overlapping with that OH peak. The CH bends at around 1400 again. And then our CO stretch this time slightly higher up at 1200 centimeters to the -1. We then look at some slightly longer molecules, so ethanal, an aldehyde. Again, if we weren't sure what the bonding in this molecule was, we could look at our IR spectrum. You can see here that we definitely don't have any OH groups. There's none of those really broad peaks. There's a few fairly sharply defined peaks, but no really broad peak. So we don't have our OH group that we've seen previously. However, we do have that very, very intense stretch at around 1700 centimeters to the -1. So that again is our CO double bond. And so if we know we have a CO double bond and no OH, then we're either talking about an aldehyde or a ketone. And typically the CO stretch is one of the most the highest intensity peaks that we get. So you can see that peak essentially goes nearly all the way down to 0 on transmittance. So you can really it's really obvious to see, very hard to miss a CO stretch, CO double bond stretch. Then there's some non-examinable ones if you're interested. So again, the CH stretches at 2900 and 2800. That's for the CH3 group. We have a CH stretch for our aldehyde group, the CHO. That's slightly higher up at 3050. And then we have a couple of bending vibrations here. So we have CH bends at 1450 and something called CH rocks. It's another type of kind of bending vibration here at 1350. And then finally, ethylamine. So now we have an amine. Now an amine stretch looks kind of similar to an OH stretch, typically slightly higher up maybe, so more centered roughly around 3400, 3500. And so we have our characteristic NH amine stretch. Again, it's very, very broad. It's very, very like an OH stretch. The reason why it can be a bit complicated for A level, but essentially it's down to the amount of hydrogen bonding. So it's why we see this broad stretch for an OH group, an NH group, but not for a CH group or a CO group. It's the hydrogen bonding that can cause this to be very, very broad. And then we have some, again, non-examinable, the CH stretches, the CH bends at the kind of standard places. Our CN stretch at 1100. Again, you can imagine that's very close to a CO stretch. If we think about those two factors that are influencing our frequency, it's our bond strength, well, they're both single bonds, a CN single bond or a CO single bond. And we also have our mass. Well, again, carbon and nitrogen are they're next to each other on the periodic table. And so the mass is going to differ by very little. And so you end up with a very similar vibration for a CO stretch as you do a CN stretch. And then there's also some NH bends occurring at about 1600. So for A level though, the key information for our purposes can be obtained really by looking at two areas. So IR spectra can often look a bit complicated, lots and lots of peaks all over the place. The worst thing you can do is sit there with your table and try and work out every single peak, or try and look at your table and try and match peaks between them. You'll be there for ages and it's not the best way to do it, because you're not looking really to identify every single peak in an infrared spectrum. You're looking to find the really key peaks. And really for A level, there's two. The first region is where we see that OH stretch, typically sort of 3200 to 3400 wave numbers. And again, it's really common to see because we have that very, very broad OH stretch. The second is from roughly 1650 to 1800. This is our CO double bond stretch. So I said it was really hard to miss. It's often the most intense thing on the spectrum. But generally, as you can see here, there's lots of other vibrations being talked about here. The CO stretch occurs really around nothing else. It's the only thing that appears in that region. So again, it's very, very hard to miss. But typically, what we're looking for really is OH stretches and CO double bond stretches. Now, this also relates actually to global warming. So one of the factors that contributes to global warming is something called the greenhouse effect. So this is where gases in the atmosphere absorb infrared radiation that's given off from the surface of the Earth. And so rather than just being lost into space, it gets absorbed by these greenhouse gases, these gases that are very good at absorbing infrared radiation, and it gets re-emitted in all directions by the atmosphere. So some of it does go back out, but some of it also comes back down to the surface of the Earth, and therefore the overall effect is to heat up the surface of the Earth. So we have our infrared radiation coming down from the sun. Some of this solar radiation is reflected by the Earth in the atmosphere. Some of it comes all the way through and it's absorbed by the Earth's surface and warms it. We then have this infrared radiation, though, being emitted by the Earth's surface. Problem is, if we have lots of these greenhouse gases, rather than just going straight back through past the atmosphere and back out into space, it actually gets absorbed by these gases and re-emitted in all directions, including back down to the Earth. And so the really key sort of problem gases for this are carbon dioxide, CO2, methane, CH4, and water vapour. And the reason for this really is because they are really strong absorbers of infrared radiation. And so very, very powerful greenhouse gases. Now, one region we haven't really talked about is towards the end of the spectrum. And we call this region the fingerprint region. This occurs below 1500 wave numbers. So below 1500 wave numbers is something called the fingerprint region. Now, typically, it's pretty complicated looking because there are lots and lots of vibrations, typically lots and lots of bends and wags and rocks, all these different types of vibrations that we haven't talked about yet, really. And so typically, it's very, very complicated. It makes assignment really of any vibrations in that region very difficult to do. However, it is actually still useful because the shape of this region is unique to every compound. In the same way that your fingerprints are completely unique to you, that fingerprint region is unique to every compound. And so if you have a database of some compounds and you want to know exactly what this compound is, you can actually compare it to a database of these spectra and you can get an exact match of the fingerprint region. It will tell you what your molecule is. And the final thing is that IR spectroscopy can be used to check for impurities pretty easily. So you might be able to do other techniques, you might be able to do some NMR techniques or maybe do a melting point test to see, but a very, very simple test to do is an IR spectrum. If we can compare the compound spectrum that we take in the lab to a pure sample spectrum, if we have one in a database, well, that can reveal the presence of extra peaks due to impurities if it's impure. Sometimes we don't even need to necessarily have a database. We can just know the structure of our compound and what functional groups are present. So let's say I have some caffeine and I want to check whether my caffeine is pure. So over on the right, I've drawn out what the structure of caffeine is. You can see we have some carbon-nitrogen single bonds, we have CH single bonds, we have carbon-nitrogen double bond, and we have a carbon-oxygen double bond as well. And so on the left, we have the infrared spectrum of pure caffeine. And you can see that generally, kind of below the 1500, that's our fingerprint region. As you can see, very, very complicated. But typically, we have that very, very sharp absorption at roughly about 1700, 1600, 1700, which is our CO double bond. So that was very easy to see. And then typically, we can see some very small peaks for what would be the CH stretches, but there's no OH group peak, there's no broad alcohol peak. However, if we look at our spectrum of my caffeine, you can see that there's a very broad peak at around 3,300, 3,400. We know that's an OH peak. Now, my caffeine doesn't contain any OH bonds, and so I must know that my caffeine, for example, has been contaminated with water. It's not dry caffeine. So, time to have a go at some questions, all to do with infrared spectroscopy. If you'd like to have a go, pause the video and the answers will be on the next slide. So, the first question I'm going to go through here is the one that was actually on the right, so the infrared spectrum of compound A, the C3H6O2. And so we have our infrared spectrum here, and we were told to identify the functional groups which cause the absorptions at X and at Y, and use this information to draw the structures of 3 possible isomers for A. So the first thing is to look at what X and Y are. X is up at about 3,300. It's very broad, and therefore we know that must be an OH alcohols stretch. Y, we can see there at roughly about 1,700. Again, that's in a region where typically nothing else is. Very, very strong intensity band. And so that must be our carbonyl, our CO double bond stretch. So we know that we have a CO double bond. We know that we have an OH single bond. And so now we know we can start drawing out the different isomers of this. And so we know we have our compound here of C3H6O2. And so I've drawn some isomers here. We have 2-hydroxypropanol. If we count up our atoms just to double check, we have 1, 2, 3, 6 hydrogens. We have 3 carbon atoms, and we have 2 oxygens. Works. We can also have 3-hydroxypropanol or hydroxypropanone. You can see for all of these that we end up with 6 hydrogens, we end up with 3 carbon atoms, and we end up with 2 oxygens. We have an OH bond, and we have a CO double bond. The key thing is that we know it's not an acid, because where our CO stretch comes, it occurs in the OH alcohols region and not necessarily in the OH acids region. Then, moving to the question that was at the bottom, the following is the infrared spectrum of one of the isomers 1, 2, or 3. We were shown the isomers on the right, and using that IR spectrum we had to deduce which of the isomers would give that infrared spectrum. So again, we need to look at what absorptions are present here. The one that really stands out is that OH stretch at roughly 3,400. So we must have an OH stretch from our alcohols in there. And then remember, the other key absorption we looked for was around 1,700. And you can see that roughly 1,700, there's no massive, very strong, sharp peak. So it doesn't have a CO double bond in it. And so therefore, really what we're looking for here is just something that contains an OH group. You can see that isomer 2 and 3 both contain CO double bonds, carbonyl groups. So it can't be those. And so therefore, it must be isomer 1. Then to say, so the question was to identify the spectrum and identify the functional group possible. Essentially, we've just done that in the first question. Also, the name of isomer 3 is not included. So if you did that, isomer 3 is pentan 2O. Remember, if we name ketones, look for the longest chain. Here it's 5 carbons long, and number where the ketone group is on carbon number 2. Thanks for watching. You can find many more videos like this on my YouTube channel. If you found the video helpful, please leave a review on the tuition website. I offer online tuition for chemistry, so you can check out those tuition pages for prices and how to contact me if you're interested. And if you need any more help with your chemistry, you can always feel free to drop me an email. I'll be happy to help.